Welcome to this comprehensive lecture on multiphase flows and instabilities in microchannels, where we'll explore the fascinating world of fluids at the microscale. Imagine two immiscible fluids flowing together in a tiny channel, creating beautiful patterns of droplets and slugs, like a liquid train with cars of different colors. Let's begin by understanding what multiphase flows are, and why microchannels create unique behavior. Multiphase microfluidics involves two or more immiscible fluids, like oil and water, flowing together in channels smaller than 1 millimeter. At this tiny scale, surface tension forces completely dominate over gravity, creating behavior that seems strange compared to everyday experience. Here we see droplets of one fluid dispersed in another fluid, separated by thin walls of the continuous phase, much like train cars separated by connectors. These systems have incredible applications in drug delivery, chemical synthesis, biological cell studies, and advanced materials manufacturing. To understand when and how instabilities occur, we need three crucial dimensionless numbers that govern the physics. The capillary number represents the balance between viscous forces trying to deform the interface and surface tension trying to keep it smooth. Mathematically, the capillary number equals viscosity times velocity divided by surface tension. When the capillary number is low, surface tension dominates, and droplets remain perfectly spherical. When the capillary number is high, viscous forces win, and we see elongated droplets and complex deformations. This graph shows how droplet deformation increases with capillary number, following a nonlinear relationship. The Reynolds number tells us the ratio of inertial forces to viscous forces in the flow. Reynolds number equals density times velocity times diameter divided by viscosity. In microchannels, Reynolds numbers are typically much less than 1, meaning flow is completely laminar with no turbulence. The viscosity ratio compares the viscosity of the dispersed droplet phase to the continuous surrounding phase. Lambda equals the dispersed phase viscosity divided by the continuous phase viscosity. Now let's explore the different flow regimes that emerge when two immiscible fluids share a microchannel. There are three main flow regimes we observe: slug flow, droplet flow, and parallel flow, each with distinct characteristics. Here we see all three regimes: slug flow with long plugs, droplet flow with separated spheres, and parallel flow with two streams side by side. In slug flow, we see long liquid plugs of the dispersed phase separated by thin films of the continuous phase. Slug flow is excellent for gas-liquid reactions because it creates large interfacial area and internal circulation patterns that enhance mass transfer. Inside each slug, we get beautiful internal circulation patterns that continuously refresh the interface and dramatically improve mixing and reaction rates. Now we address the fundamental question: when does a smooth coflow become unstable and break into droplets? Imagine two immiscible fluids entering a microchannel side by side, initially flowing in parallel with a smooth interface between them. The interface can remain stable with parallel flow on the left, or it can destabilize and break up into droplets on the right. Whether the interface remains stable or breaks up depends on the flow rate ratio, the viscosity ratio, and the channel geometry, including width and shape. We can define a stability parameter as the product of capillary number, flow rate ratio, and viscosity ratio. When this stability parameter is low, the parallel flow remains stable with a smooth interface that doesn't break up. When the stability parameter exceeds a critical value, the interface becomes unstable and spontaneously breaks up into droplets or slugs. Let's understand the physical mechanisms that drive interface breakup in microchannels. The relay plateau instability occurs because surface tension always tries to minimize interfacial area, favoring spherical droplets over cylindrical threads. A cylindrical thread develops small perturbations that grow over time, eventually pinching off into separate droplets to minimize surface energy. The critical wavelength for this instability equals 2 pi times the thread radius, determining the characteristic droplet spacing. At high viscosity ratios, we observe tip streaming, where elongated threads are continuously pulled from the dispersed phase droplets. As we increase flow rates, the system transitions from a dripping regime, where droplets form quasi-statically, to a jetting regime with continuous thread extension. Fingering instabilities create fascinating patterns when one fluid displaces another in confined geometries. Fingering instabilities occur when a less viscous fluid tries to displace a more viscous fluid, creating finger-like penetration patterns. We see fingers radiating outward from the injection point, creating patterns that look like a starburst or tree branches. The onset and morphology of fingering are governed by the viscosity ratio and the capillary number of the system. Fingering occurs when the viscosity ratio is less than 1 and the capillary number exceeds a critical threshold value. Phase diagrams help us predict which flow regime will occur for given operating conditions. This phase diagram plots dispersed phase flow rate against continuous phase flow rate, showing distinct regions for slug, droplet, and parallel flow regimes. The exact boundaries between regimes depend on channel dimensions, viscosity ratio, and interfacial tension between the two fluids. These diagrams are typically constructed from experimental measurements, where researchers systematically vary flow rates and observe regime transitions. We can also plot stability boundaries in capillary number versus Reynolds number space, separating stable and unstable flow regions. Scaling laws allow us to predict droplet sizes and frequencies from operating parameters. The size of droplets produce scales primarily with the channel width and the ratio of dispersed to continuous phase flow rates. A simple scaling law says droplet length over channel width equals 1 plus alpha times the flow rate ratio, where alpha is a geometry-dependent constant. The frequency of droplet generation increases linearly with the total flow rate through the junction. Frequency equals the sum of flow rates divided by the average droplet volume, giving a direct relationship. Experimental data points collapse onto a master curve when we plot normalized droplet length against flow rate ratio, confirming the scaling law. Let's explore a key application, using slug flow for enhanced gas-liquid chemical reactions. In this application, long gas slugs alternate with liquid plugs that contain dissolved reactants and catalysts. Gas bubbles provide reacting gases like oxygen or hydrogen, while liquid plugs contain the reaction mixture with internal circulation. The internal circulation in each liquid plug continuously refreshes the gas-liquid interface, dramatically enhancing mass transfer rates. The volumetric mass transfer coefficient can be measured from the concentration evolution in each slug over its residence time. This configuration provides high interfacial area per unit volume, uniform residence time for all liquid elements, and eliminates backmixing that plagues conventional reactors. Another important application is using segmented flow to supply oxygen to cells growing in microfluidic devices. Living cells have a continuous metabolic demand for oxygen, and insufficient supply leads to hypoxia and cell death. Cells suspended in culture medium flow through the channel, with periodic gas bubbles providing fresh oxygen by diffusion. Periodic gas slugs act as mobile oxygen reservoirs, continuously replenishing dissolved oxygen consumed by cellular metabolism. The refresh time between oxygen pulses equals the slug length divided by the flow velocity. System design must balance cellular oxygen consumption rate against the frequency of gas slug arrival to prevent oxygen depletion. Modern computational methods allow us to simulate these complex multiphase flows with high accuracy. The volume of fluid method uses a color function to track the interface position throughout the computational domain. The volume fraction F is advected by the velocity field according to this transport equation. The level set method represents the interface as the zero contour of a signed distance function that measures distance from the interface. The computational domain is discretized into a fine mesh, where the governing equations are solved numerically at each time step. Simulations reveal detailed information about droplet formation dynamics, internal pressure distributions, and velocity profiles that are difficult to measure experimentally. Specialized experimental techniques are needed to observe and quantify these microscale phenomena. High-speed microscopy with frame rates exceeding 10,000 per second can capture the rapid dynamics of droplet breakup and coalescence. Sequential frames show the evolution from a single droplet to elongation to final pinch-off into two separate droplets. Microparticle image velocimetry seeds the fluid with tracer particles and tracks their motion to reconstruct detailed velocity fields. Miniature pressure sensors integrated into microchannels can measure the pressure variations associated with slug and droplet passage. Designing robust microfluidic systems requires careful consideration of multiple factors to ensure stable operation. The surface chemistry of channel walls controls wetting behavior and contact angle, which strongly influences flow patterns. The Young equation relates contact angle theta to the surface tensions at the solid gas, solid liquid, and liquid gas interfaces. Maintaining stable flow rates using precision pumps is crucial to prevent unwanted transitions between flow regimes. Stable operation produces droplets with uniform size and spacing, while unstable conditions lead to irregular patterns with varying droplet sizes. Temperature variations change fluid viscosity and surface tension, potentially causing drift in operating conditions over time. Beyond two-phase flows, three-phase systems with gas, aqueous, and organic phases create even richer phenomenology. Three-phase segmented flow alternates gas bubbles with organic and aqueous liquid slugs, enabling multi-step reactions and extractions. Three-phase systems enable complex multi-step chemical syntheses, liquid-liquid extractions, and separation processes in continuous flow. The main challenge is controlling three different interfacial tensions simultaneously while maintaining stable flow patterns. At higher flow rates, we transition from dripping to jetting, where a continuous thread extends before breaking up. In jetting mode, a continuous thread extends from the nozzle and breaks up downstream into a train of uniform droplets. The Weber number, representing inertial to surface tension forces, governs the dripping to jetting transition. When the Weber number exceeds a critical value around 1, the system transitions from dripping to jetting mode. The characteristic breakup timescales as the square root of density times radius cubed over surface tension. Droplet coalescence can destroy desired flow patterns and must often be prevented through various strategies. Coalescence happens when the thin continuous phase film separating two droplets becomes unstable and ruptures, allowing them to merge. The thin film between droplets can rupture due to various factors like surface tension and hydrodynamic forces, leading to coalescence. To prevent unwanted coalescence, researchers use surfactants to stabilize the interface or control the flow conditions to minimize droplet interactions. Surfactants reduce the interfacial tension between the droplet and the continuous phase, making it harder for the film to rupture and coalescence to occur. By adjusting flow rates, channel dimensions, and geometries, researchers can control the flow conditions to minimize droplet collisions and coalescence.